So here's my implementation, which should be relatively straightforward. We have a value function that's of the same size as my world, and I initialize with 99 everywhere. This has to be a value that's large enough it doesn't conflict with any actual value. I now update the value function a number of times. I don't know how often, but as long as I change something, I update it. Therefore, I introduce the variable change, which is set to true in the beginning, and while change is the case, I update. But it immediately set change to false, and the only way to come back to true is that I actually changed something. Now, I go through all the grid cells in a fixed order. Happens to be not very efficient, but certainly gets the job done. I first check if the grid cell I'm considering is the goal. And here is a typical case where I check for change. If the value is presently correctly set to 0, I don't do anything. But if it's larger than 0, it is 99, then I set it down to 0, and I've just changed something. So therefore I set the change flag back to true. If it's not a goal cell, then here's my full update function. I go through all the actions. I project a potential next state upon executing an action by adding the corresponding delta to the x and y. That gives me x2 and y2. I test whether x2 and y2 are legitimate states. For that, they have to be inside the grid. So I check whether the numbers are larger than 0 and smaller than the dimension of the grid. And it has to be an actual navigable grid cell. So therefore, I check whether the coordinates in the grid has a 0. If that's the case, I can propagate back the value. My new value is the value of this future grid cell plus the cost per step, which happens to be 1. Now, if this value is better than the value I have already, which means it's smaller, then I assign this new value to my original grid cell x and y, plus, of course, the cost step. And then I know I've changed something, so therefore I set change to true, and the procedure repeats. The only thing missing at the very end, when I'm done, I print out the value function using these commands over here. So I should warn you, this is not very efficient. And the reason why it's not efficient is that value slowly propagates from the end towards the beginning. But leaving this concern aside, it actually computes the correct value function. There's ways to make it more efficient. It's also interesting to see what happens if I cut off any path to the goal, and then the resulting value function will retain 99s for most of the state variables, exactly those where there's no valid path to the goal.